Okay, so we saw, or I stated the result, that as long as we have a separation oracle, which can be defined in fixed point with counting for some family of linear programs, for some family of polytopes, if you will, then the corresponding optimization problem can itself be solved in FPC. And I'm going to skip over the details of how this is done. It's an interesting but somewhat technical definition, which you'll find in a couple of slides that are available in with this course, but I will skip over the details for now. Instead, I'm going to go on and discuss one of the consequences of this, namely the fact that we can define the existence of perfect matchings in graphs in FPC. Now, the graph matching problem has popped up several times in the course of this course of lectures, and now we'll discuss it a bit formally and see why it turns out to be FPC definable. So recall that in a graph, GVE, not necessarily a bipartite graph, a matching is a set of edges such that each vertex is incident on at most one edge in M. And it's a perfect matching if each vertex is incident on exactly one edge in M. Now, we saw early on that the existence of a perfect matching is not definable in fixed point logic. This is fixed point logic without counting. In fact, even in bipartite graphs, it's not. In the case of bipartite graphs, it was shown that it can be defined in FPC by Blaskorevich and Shella back in 1990. And they conjectured that this was not the case for general graphs, that the FPC definition which worked for bipartite graphs could not be extended to general graphs. Turns out that conjecture was false, and this was refuted as a result of the work on linear programming in FPC. So we're going to consider the more general problem of determining the maximum weight of a matching in a weighted graph. So a weighted graph means we're given a graph G equals V with weights, which assigns to every edge a non-negative rational number. And note, actually, when we're considering weighted graphs, there's no need to have specifically a set of edges. We can simply assign a weight to every pair of vertices and treating it as assigning it a weight of 0 if the edge is absent. Also note that the problem we're talking about is determining the maximum weight of a matching. We can't expect in FPC or in any logic to actually define a maximum matching, as in to return the set of edges which form a maximum weight matching, because this is simply not invariant under the symmetries of the graph, right? For instance, if G is a complete graph, it has an exponential number of different maximum matchings, and all of them are obtained from each other by permuting the vertices according to automorphisms of the graph. So there is nothing you can do. You can't pick out one particular maximum matching, but what you can do is determine what the weight of a maximum matching is. So the matching problem can be expressed as a linear program, and Edmonds showed that the problem of finding a maximum weight matching can be expressed as the following linear programming problem. We've already seen this before, except I've now phrased it in terms of weighted matching. And now here we explicitly have a graph given. So what is this? How should we read this? So y is our set of variables. Think of it as assigning a value 0 or 1 to an edge where we want to, 1 indicates that we include that edge in the matching. So this quantity here, the dot product of the weight with the vector y, is simply the weight of the matching, if y is in fact a matching. And these are constraints intended to ensure that the vector y is in fact a matching. This here, A is the adjacency matrix of the graph. matrix of G. So this constraint really says that Y picks out at most one edge incident on any vertex V. This says that the weight assigned to any edges is non-negative. And this is the sort of, comes from the matching polytope we saw earlier. It really says that for any odd size set of vertices, if you look at all the edges inside this, then the number of edges chosen in the matching is at most half of W minus 1, right? In some sense, it has to be strictly less than half of the number of vertices, right? So inside any odd size set, the number of edges in a matching must be strictly less than half. Okay. And now it's not at all obvious, but what Edmund shows is that what this defines is exactly the maximum matching problem. What we want to do is now a separation oracle for this polytope, right? So this polytope, as defined, has an exponential number of facets. We know this because there's one such constraint for every odd-sized subset of the vertices. And we want a separation oracle. What does that mean? That means we're just given the graph G. We're not given this linear program explicitly. And by an FPC interpretation from the graph G, given the graph G and any vector Y, the FPC formula will determine whether Y satisfies all those constraints. In other words, it is a matching. And if not, then give you a separating hyperplane. A consequence of this is that there is an FPC formula defining the size of a maximum matching. And as I already noted, it doesn't allow us to define an actual matching, but it does allow us to determine the size. And so in particular, we can write an FPC formula that determines whether there exists a perfect matching. In other words, a matching whose size is exactly half the number of vertices in G. So in order to get to this result of we proceed through a series of steps which are rather interesting in themselves. They're sort of classic problems in graph algorithms which we show along the way are FPC definable. The first one is the max flow problem. Okay, as I said, a very classic algorithmic graph theory problem. We're given as input a weighted graph. Again, now forget about the set of edges. We just think of it as a set of vertices and a capacity. We could a weight, we just call it a capacity, which assigns to every pair of vertices a non-negative rational number. And we have a source and a target. Okay, so this C is supposed to describe the capacity of the link between, right? So C of xy is the capacity of the link between vertex x and vertex y. Maximum flow you can take from x to y. And what we want to know is what is the maximum flow you can get from the source to the target through the whole graph. So formally, we're looking for a flow which assigns to every pair of vertices a non-negative rational, the actual flow. It has to optimize, in other words, or maximize this, which is the flow into the target T, right? So you take over all vertices V. The flow coming into T minus the flow going out from T towards V. That is the total net flow into the target. Subject to these constraints, this says that everywhere apart from the source and target, the net flow is 0 at every vertex. And the flow along any edge, if you will, any pair UV, is between 0 and the capacity of that edge. Okay? So that's what the max flow problem is. Claim is you can express this in FPC. In other words, I give you a capacitated graph. You can determine the value of the max flow. And the reason is simple. It is that, well, I've just explicitly given you a linear program. And this linear program is explicitly given. And hence we can just use the ellipsoid method. We don't need a separation oracle as such. this, as it were, this linear program can be constructed from the capacitated graph trivially in FPC. Okay. The next, closely related to max flow, is the min-cut problem. Again, the input is a capacitated graph and a source and a target. And now what we're looking for is a cut. What is a cut? It's a set of vertices which contains the source but doesn't contain the target, right? So in our graph, we have a source S and we have the target T, and really we're looking for a cut. So we call this side of the cut C, and that is a complement of C. So S is in the set C and T is in the source. And what we want to do is minimize the total capacity across this cut. So for all U in C and V in its complement, you take the capacity from U to V. That sum is the value of the cut, and we want to find the cut with minimum value. Claim again. You can define this in FPC. In other words, there's an FPC formula which, interpreted in a capacitated graph, will give you will actually define the set C. Okay, now this is a bit more than just saying the value of the minimum cut. You can define the set C. This is not at all obvious that there is even a canonical cut C, but we can show this because the idea is you can compute the max flow, and associated with the max flow, you can define the set of those vertices for which there's a path from the source S to the vertex V with non-zero capacity in the residual graph. What is the residual graph? This is the graph G where you subtract from every pair UV, you subtract from its capacity the actual flow. So in other words, this is the capacity remaining once you've pushed through the flow. And this then is the set of vertices which still have capacity, non-zero capacity, for flow from S to V. Now, the max flow min-cut theorem tells us that the capacity, well, by definition, the capacity out of this set is 0 in the residual graph. So in the original graph, it is exactly F. But what we're able to show is that actually this set is canonical independent of the particular flow, right? There may be more than one flow that gives you, that achieves the maximum, but the choice, this is a canonical minimum cut, which is in some sense of all cuts of this value, the one that's closest to S. So we can define this minimum cut, it turns out, in FPC. Next is the notion of a minimum odd cut. So now we're given a capacitated graph, again, and assume that the number of vertices is even. An odd cut, a minimum odd cut, is simply a cut which is of odd size, right, and minimum value among all odd cuts. But note, here we don't have a source and a target. Rather, we are saying, take any odd size subset and look at the capacity leaving that. That's the value of the cut. And we're looking for all, for any odd size subset of G, right? So this is the point why it's important that V is even. Otherwise, there is a trivial cut of size 0. Now, what we show is that there is some pair of vertices, S and T, such that the canonical minimum ST cut is in fact of odd size. Okay? And it is a minimum odd cut then. So you get a minimum odd cut simply by essentially iterating over all pairs of vertices ST and computing the minimum ST cut and checking whether it's of odd size. Now, again, this might not be canonical, it might not be unique, but you get you can define a small set of them, small meaning polynomial size. There are at most n squared of these that you will get by this process. Okay. Why is this important? Well, we use this now to solve a rather generalization of matching, which we call B matching. What is B matching? So you're given a graph. Think of the A now is the incidence matrix of the graph, right? So between vertices and edges, it tells us the incidence. We're given a vector B of numbers, which indexed by the vertices. And the idea is we're looking for a B matching, which what really means we're looking for a set of edges where the number of edges, a subset of the edges of E, where the number of edges incident on a vertex V is exactly BV. Okay, so a matching is the special case when B is the all ones vector. And C is edge weight, if you will, or capacity as we call it. So we're looking for a maximum weight matching or a maximum weight subgraph of G where the degree in the subgraph of every vertex V is given by this vector B. Formally speaking, we're looking for a vector Y which maximizes the weight. I mean, think of this again. I say non-negative integers, but think of this as Y as a 0, 1 vector. It's a bit easier. So this is simply the so Y is a subset of the edges. This is the weight of that subset. This condition says really that every vertex has at most B edges in Y incident on it, and this is simply saying Y is not negative. As I said, taking B to be the all ones vector and C to be the all ones vector, in other words, uniform weight, means we get the maximum matching problem. If we relax this to get a linear program, meaning instead of asking for integer solutions, we ask for rational solutions, and we add the usual constraints about for the matching polytope, an exponential collection of constraints, then we get a linear program which gives us the convex hull of the matchings as before. Okay, so this is the problem we aim to solve. And what we use is this classic result of Padberg and Rao from optimization theory. If you're given a vector indexed by the edges, then you can construct a capacitated graph H such that Y violates an odd set constraint. So this is by an odd set constraint, I mean one of these. Okay, so Y violates an odd set constraint if and only if H has a minimum odd cutoff value less than 1. So in other words, you're given the original graph and you're given a vector Y, right? We don't have an explicit representation of this exponential size polytope, but this is essentially our separation oracle, right? From Y and the graph, we can construct this capacitated graph. We check if it has a minimum odd cutoff value less than 1, and that tells us that Y violates a constraint, and from H, in fact, you can extract such a constraint. So what we need to show is that, this H is obtained by what's known as the Gomori-Hu tree of the graph. We can define H from Y in the graph. We can define a small set of minimum odd cuts. I've already sort of argued that we can do that for any graph. From that, we can define a small set of violated odd set constraints, and then construct a canonical violated constraint by adding them all up. Okay, a number of steps, which I'm not going to go into in detail, but the next conclusion is that there's an FPC interpretation which, given this matching polytope and a vector, gives you the separating hyperplane. So in other words, we can express the separation oracle for graph matching. And from that, the definability of graph matching in FPC follows. Okay, with that, I'm going to turn to a final topic for this lecture, which I will do rather briefly. And I will talk about symmetric linear programs, right? I alluded to this at the beginning. Brief recap. I talked about the Yannakakis approach to symmetric linear programs, where we were trying to symmetrically define an extended formulation of the convex hull, such as the TSP or matching polytope. And I said if you relax from the convex hull, if you relax the symmetry condition, you still have exponential lower bounds. If you also then relax from the convex hull to just deciding matching, you get something equivalent to the P versus NP question. And I said we would consider the case where we relax from convex hull to the decision problem, but we keep the symmetry condition. And there we're able to prove, we're going to prove equivalence with symmetric circuits and counting logic. So roughly speaking, I mean, I stated the equivalence of those three formalisms right at the beginning. To be precise, what we prove is for any size, up to, some sub-exponential bound, if you have a symmetric circuit of size S, say on graph, you can translate it to a symmetric linear program of size polynomial in S. And in the other direction, if you have a symmetric linear program of size S, you can translate it to a formula in first order logic with counting, where the number of variables is order log S divided by log n. So in particular, if this is polynomial, this is constant. And this, we already know that you can take a family of formulas like this with a constant number of variables and translate them into circuits of size polynomial in the size of the formula. So that completes the three-way equivalence between circuits, linear programs, and formulas. Okay, so I want to give you a very rough idea of how these two statements are proved. The translation from circuits to linear programs, I've already described the one that Yannakakis gave, where we simply add new variables for every gate in the circuit. But you have to do it a bit more carefully because, first of all, we have to account for threshold gates and we have to preserve symmetries. And it requires some work, but it is possible to achieve these two feats simultaneously. And this is one thing we show in the paper. It's the other direction in some sense, which is more interesting, and it kind of connects with the themes we've looked at. So if you start with a linear program, say we're given a linear program which defines a symmetric polytope, Q, right, in Qx times Qy, where x is n times n, and symmetric means precisely that any permutation of n extended in its action to x, for any such permutation, there is a permutation of y, which gives you back the same polytope. So, take the action of Sn, it induces now an action on y, and partition y into orbits under this induced action. So the first step is that you can just take each of these orbits and make it into a single variable just by linearity. And this gives us what we call a reduced linear program, which is equivalent to the program P, but it is rigid in the sense I used rigid when I talked about symmetric circuits, namely, now for every permutation in Sn, there is exactly one permutation of y which extends it. I should say we don't know that we can do this in polynomial time. So in the case of circuits, I told you we can convert to a rigid circuit in polynomial time. We don't know how to do this in the case of linear programs. And this is the key step why we can't guarantee that if we start with a P uniform family of linear programs, we get a P uniform family of formulas or circuits. But we only state the result for the non-uniform case, so we don't need to worry about that. Okay, so we have now this reduced rigid P hat. It defines a rigid symmetric polytope Qx and, on the set of extension variables Q hat. Say we're given a graph on n vertices. this, in some sense, gives an actual value to these variables x, right? So we can now replace every variable with an actual value. This, the program is in some sense defining a, it's like our circuit. It's expecting as input a graph. The graph gives actual values to these variables x, so we can substitute for them values 0, 1, right? How do we do that? Well, we have to fix a bijection between the vertices of the graph and this n. So in other words, each variable xij in x gets assigned, each I and each j is assigned a vertex in G, and this variable gets value 1 if that's an actual edge in G and 0 otherwise. But note this depends upon the choice of the bijection beta. Each such bijection, once you've put values for all the variables in x, what you're left with is a linear program in just the variables y hat. We call that q beta because it depends on the choice of beta. But what symmetry tells us is that up to permutations of the variables y beta, well, y hat, all of these are the same, q beta. And what we want to show is we can obtain an equivalent linear program, equivalent to q beta, from the graph G directly by a, if you will, an FPC interpretation or a CK interpretation. We're considering it more generally because we're letting S, be bigger than polynomial. But a CK interpretation from the graph G with advice p hat. What do I mean by advice p hat? Think of, we're given the graph G, and on the side we have a domain of numbers, like we do with fixed point weight counting. And the linear program p hat is some sense is given by some relations on this ordered domain. So we're able to read what the program is. Okay, so given this and this representation of p hat, we can define a linear program equivalent to q beta. Okay, it's equivalent. But independent of the choice of beta, because all of these are equivalent. The key element, again, as with the translation from circuits to formulas, is to show that each variable in y, just like every gate in our circuit, has small support in the sense that the stabilizer group of the variable under the action of Sn on y, this should be y hat. So every variable and every constraint has a support which is small. Again, order log s over log n. We used, when we were talking about circuits, we used this fact from permutation groups that whenever you have a subgroup of Sn of small index, something like n choose k, then it has a small set such that all even permutations which fix this set are included in G. So in other words, as I put it, G contains a large alternating group. To get to small supports, we had to replace this with a symmetric group, which in the case of circuits, we did by an inductive argument on the structure of the circuit, showing that you couldn't get a case where you had a large alternating group but no odd permutations, which fix that set. That inductive argument isn't available to us in linear programs because the linear program, the set of which is the set of variables y and the set of constraints, simply doesn't have that acyclic structure, which allows us to do an induction starting with the input gates and going through. So instead we use an alternative method. We show that if there is some variable in y, and similarly if there's any constraint which does not have small support, then we can construct from this linear program a small graph, small meaning polynomial in S, whose automorphism group is exactly this alternating group. Exactly meaning isomorphic to. And this leads to a contradiction because it's known by a theorem of Liebeck that the smallest graph whose automorphism group is isomorphic to an alternating group AN has size exponential in N. Okay. Now, this is sort of, a magical black box we pulled out of the literature, which avoids the inductive argument, which we did in the case of circuits. We could have applied this in the case of circuits as well. There was no need for that, but I just thought the induction was a cleaner one to present there. Okay. And that completes the sort of sketch of the proof that the three models, symmetric circuits, symmetric linear programs, and formulas of counting logic really give us the same non-uniform thing. And in the uniform case, we can add this relational machines we've looked at. So we've got machines, circuits, linear programs, and logic. Now I think we've got sort of the pillars of a really solid, robust notion of symmetric computation with, thanks to bijection games, a reliable method for proving lower bounds. And that's where we'll stop for this lecture.